Hello, my name is Diego Sanchez, and I'm an undergraduate student from New Jersey Institute of Technology, working with Gareth Perry, also of the New Jersey Institute of Technology. And this project is on using citizen science and amateur ham radio to observe traveling ionospheric disturbances. Traveling ionospheric disturbances are propagating variations in ionospheric electron densities that affect radio communications, and it can help with understanding energy transport throughout the coupled magnetic sphere ionosphere neutral atmosphere system. TIDs may be generated by disturbances from space or from perturbations from the neutral atmosphere. TIDs also often propagate over very large distances, making it difficult to identify their sources and track the evolution of their development, but they can be remotely sensed using ground-based radio instrumentation. Some of the instruments used in detecting traveling ionospheric disturbances include the Superdual Auroral Radar Network, or SuperDARN, GPS, and ionosons. However, the scope of these instruments is rather limited. Recently, it has been shown that observations of amateur ham radio communications, voluntarily built and operated by the ham radio community, can be used to measure ionospheric impacts of space weather events such as solar flares, geomagnetic storms, and solar eclipses. These observations present unprecedented opportunity to use citizen science observations to advance our understanding of the geospace environment, thanks in particular to the existence of large datasets generated by systems such as the Weak Signal Propagation Reporter Network and the Reverse Beacon Network. Ham radio detects TIDs in a similar way to how SuperDARN ionosons and other radio science instruments detect them. As the ionosphere becomes perturbed by a passing TID, the amount of refraction an HF signal experiences changes, which results in a perceived fading in HF propagation. Radio frequency refraction is determined by the density of the ionosphere, and since different frequencies refract at different ion densities, changes in the total electron content caused by TIDs are expected to show as dropping or growing numbers in total successful ham radio connections in the WhisperNet and RBN data. The ham radio observations are represented by 2D histograms. The data is separated into 2-minute bins over a 24-hour period measured in UT time, while the y-axis represents estimated propagation distance and spot density is represented by yellow colors. The SuperDARN plots are the easiest to compare to the ham radio plots, since the wave-like structures present in them when there is a TID passing through should be very close, given that they both use the ionosphere's refracting capabilities on HF signals in very similar ways. We can see the similarities of these two plots especially well for the 3rd of November 2017. GPS total electron content plot comparisons are a little trickier. In the GPS TEC plots, radio range is shortest when the TEC is red and shorter when it is blue. The highest peaks in the ham radio histograms should correspond with deeper blue colors in the TEC plots, while the lower peaks in the ham radio plots should correspond with deeper red colors in the TEC plots. And this is exactly what we find happening when comparing both plots for January 26, 2017. Ionosons work by sending a sweeping array of radio frequencies straight up to the ionosphere and recording the frequencies that bounce back. The highest frequency that the ionoson reflects is called the FOF2. The higher FOF2 frequency, the higher the electron density will be, thus there will be more refraction at higher FOF2 values. This means that the periodic oscillations present in ionoson data in the presence of a TID should be inversely proportional to those observed in ham radio data. This stays consistent when observing the plots for January 26, 2017. These results show the incredible potential that ham radio citizen science holds for the scientific community. The consistency shown when comparing ham radio plots against other known instruments that are used in the detection of TIDs shows that RBN and WhisperNet can be used as tools for monitoring TIDs. However, it isn't without limitations. The most prominent frequency that is capable of showing TIDs and the ham radio plots is 14 MHz, and 14 MHz communications become nearly impossible in the nighttime, making tracking TIDs at night more difficult. It also doesn't shed light on the exact mechanism responsible for the TIDs. The current method of detecting these TIDs in ham radio plots is also purely visual. This is incredibly inefficient given the volume of WhisperNet and RBN data, and developing an automated mathematical approach to detecting TIDs is required. This, along with finding the exact mechanism, are reserved for future work. Thank you, and I hope you all enjoyed.